Hello, today we are talking about rotational dynamics. Last time in class we talked about rotational statics or static equilibrium, where the net force and the net torque were both zero. In rotational dynamics that is not necessarily the case. If your net torque is not zero, then you have angular acceleration for your object. If the net force is not zero, then you have some tangential acceleration on your mass. Let's take a look at our first example here. It says a disk with a mass of 5 kilograms has a radius of 2 meters and there is a 10 Newton force acting on that disk. Draw a little picture down here just so we get a good idea. We've got our disk here. I know it's a good disk. It has a radius r of 2 meters. There is a force acting on this disk like so, and the disk has some mass m. Notice right away that this force, there's no way these are going to be a net torque of zero. Okay, there's going to be angular acceleration. It is going to be rotating. Our first thing to find is the angular acceleration of the disk, and we're going to do that by setting up a net torque equation. So the net torque is not zero in this case. It's going to be equal to the moment of inertia, or rotational inertia, times the angular acceleration. And we also know that the other equation for the net torque is the sum of all the forces perpendicular to the lever arm or the radius times their distance from the axis of rotation. So in this case, our distance from the axis of rotation is r, and that perpendicular force to that is just F, and that's still equal to moment of inertia times angular acceleration. We can plug in some values here. We know that the radius is 2 meters, the force is 10. The moment of inertia is a little tough. We know from our list of moment of inertia that the moment of inertia for a disk or a pulley is 1/2 times the disk's mass, which in this case is 5, times its radius squared. And you can go back to the moment of inertia notes for that. So this is 2 squared, and then that's still multiplied by the angular acceleration there. Little quick algebra, and we get that the angular acceleration is 2 radians per second squared, and there's our final answer. Okay, there is a net torque because there's only, I shouldn't say there's only one force, there's only one torque acting on it, or the net torque isn't zero, and that results in an angular acceleration. Next up, part B says find the tangential acceleration of the point at the edge of the disk. So for a point down here at the edge of the disk that's r distance away, that tangential acceleration is going to be equal to the radius times the angular acceleration. So this is a radius of 2, our angular acceleration was 2. We end up with a tangential acceleration of 4 meters per second squared. Remember, anytime we have one of the rotational kinematic variables, we can multiply it by the distance from the center of the axis of rotation. We get that tangential component there. Part C says, what is the angular velocity of the disk the instant it is moved through 20 revolutions? Some of that rotational kinematics we struggled with earlier. What do we know? We know that the angular acceleration is 2 radians per second squared. We know that it starts from rest, so the initial angular velocity is 0 radians per second. Says that it goes through 20 revolutions. I don't want revolutions, I want that in radians, so that means my theta here is going to be 20 revolutions times 2 pi. Oops, that's a pi. So that's going to be 40 pi theta there, 40 pi radians. And then we're looking for final angular velocity. So I know from my rotational kinematics that this is the easiest equation to use. And we're solving for this final angular velocity here. So we get final angular velocity equals 0 plus 2 times our angular acceleration of 2 radians per second squared times 40 pi, which is the angular displacement we had. And if you plug all this in and do a little algebra, you are going to get, actually this isn't going to work, you're going to get that the angular acceleration is equal to 22.4, and that's going to be in radians per second. Struggling to keep that in there. So we did a little bit of rotational kinematics. We knew the angular acceleration, the initial angular velocity, and we found the angular displacement. and we were able to come up with our final angular velocity of 22.4 radians per second. Next up, we're solving for the tangential velocity. Same as before in part B. We're looking for the tangential component. We know the angular component. So this is going to be tangential velocity equals the radius times the angular velocity. So this is 2 is our radius. The angular velocity is 22.4 radians per second. So we are going to get a tangential velocity of 44.8 meters per second. Don't forget your units on there. Lastly on this problem, part E, we're looking for the centripetal acceleration at this same point. So we can imagine this point going around. Centripetal acceleration has been kind of tough for us. It's related to the centripetal force, which is the force that causes the object to continue moving in a circle. Centripetal acceleration we like to subnote with a little c, and we should remember that this is v squared, that tangential velocity, divided by the radius. So 44.8 meters per second, we're squaring that, and that's divided by the radius of 2. And if you calculate this out, you get about 1,004 meters per second squared. Big idea that you should look back at here is that the net torque is not 0, that has a net torque, so it's going to be angularly accelerating. That's what we found in part A, and then the rest of these was really rotational kinematics. So kind of a review for you guys. So that is number 41. Alright, on to the next problem. We have a rod attached to a wall that's able to pivot about an attachment point with the wall. The string is attached and it holds the other end of the rod. Okay, at this very moment, it's in static equilibrium. The net force is 0, the net torque is 0. The rod has a mass of 5 kilograms and a length of 2 meters. The string makes an angle of 30 degrees with the rod, and then the string is cut. And what we want to find, it doesn't have anything to do with the tension in the string or anything like that, not this time. We want to determine the acceleration of the rod the instant the string is cut. So the tension's no longer there. What is that angular acceleration going to be on the rod? So this is a net torque problem. We're going to start out and we're going to say, hey, the sum of all the torques here, this is equal to the moment of inertia times the angular acceleration. We know that this net torque on this rod is going to be the sum of all the perpendicular components of the forces multiplied by each of their distances from the axis of rotation. So here's our axis of rotation. After this is cut, the only force acting on the rod is going to be this force of gravity that's acting from the center of mass there. So this is going to be the distance that force of gravity is from the axis of rotation, and that's going to be equal to the moment of inertia times angular acceleration. If we keep going here, the moment of inertia, this has to be for a rod fixed about an end. And if you flip back a couple pages on your notes, you'll see that the moment of inertia for a rod rotating about its end is 1/3 times the mass times that distance squared, and we still have angular acceleration here. So let's start plugging in some numbers. This distance right here is half of the total length of the rod. The total length of the rod was 2, so this distance is 1 meter. The force of gravity is mass times gravity, so that's going to be 5 times 10. We have 1/3. Again, the mass is 5. That radius is 1. We're squaring that, and we've got alpha here. So the angular acceleration is 7.5 radians per second squared. That would be our final angular acceleration. Now, this angular acceleration is only that for an instant. As soon as this rod moves a little bit, the perpendicular component of the force changes just a little bit, so that's going to keep changing. That's where calculus comes involved, and we don't really have to worry about that. If this problem were asking for the tangential acceleration, we could just multiply this by the radius and get the tangential part of that acceleration instead of the angular part. But that is number 42. Number 43 asks, after solving for the acceleration of the rod, it seems that kinematics would make sense to solve for the rod's speed. Why does this not work, and why is energy the only way to solve this problem? And I kind of alluded to it just a moment ago when we were talking about 42, that we can't use kinematics because the angular velocity isn't going to stay constant. This force of gravity right here isn't always going to be completely perpendicular. we always have to use the force of gravity, the perpendicular component to it. So for the very first instant that the string is cut, the force of gravity is perpendicular. But later on, when the rod is down here, the force of gravity is no longer perpendicular to that. So since this force of gravity, since the perpendicular component to that is always changing, we can't use it for any rotational kinematics because that results in a non-constant acceleration. And for our purposes in class, we're only going to do calculations that involve a constant acceleration. Alright, this next problem is a bit of a doozy. Number 44, we've got a ball that is a mass of 2 kilograms, radius of 50 centimeters, so that's a half a meter. Don't forget to change your units to meters. And rolls 10 meters along a 30-degree incline. We've done problems like this before, but we haven't dealt with where there's friction and the ball's actually rolling as opposed to just sliding down. Part A says, draw a free body diagram for the ball if the ramp is frictionless. This one's pretty simple. We're used to this. We have the center of the ball here. The force of gravity is acting down. And then the normal force comes out like this and pushes up on the ball. And then typically what we do is we break these into components and we deal with parallel components and perpendicular components, and we work out the problem. Part B wants us to draw a free body diagram if the ramp is rough, and that means there's going to be friction. So you still have the force of gravity acting from the center here, and you've got this normal force that comes up from the ramp, but then at this point here where the ramp touches the ball, there is going to be friction. And if there's no slipping, this friction is actually static friction. Even though the ball is moving, at that point right there, there's static friction acting on the ball. Now part C says, using force and kinematics, stuff back from September, October, November, determine the translational speed of the ball at the bottom of the incline. We could probably actually do this with conservation of energy, but it tells us to do force and kinematics, and so we're imagining the ball just slides down frictionless. It doesn't even have to be a ball, it could be a block because there's no friction, it's not rolling, it's just going to slide down. In order for it to roll, there would have to be friction. So I'm going to redraw this diagram here. I'm going to use a different color, but we're going to look at the ramp, and here's our ball, and we're going to break this into components. So here's your normal force, and then this would be mg cosine theta, and then we've got the parallel component here, which is mg sine theta. Okay? And we want to figure out what's the velocity at the end. So we're going to use forces. We're going to do the net force in the parallel component is equal to mass times acceleration. And that force that's acting in the parallel component, that is the parallel component of the force of gravity. So mg sine theta equals ma. Those masses cancel out. We get acceleration equals 10, which is gravity, times the sine of 30 degrees, or 5 meters per second squared. So we now used dynamics, we used forces to find the acceleration, and then we're going to use that acceleration in kinematics to figure out what's the velocity at the end of the ramp. I'm trying to think if there's a simpler way to do this than what I did last time. There definitely is. We could use this equation right here. Final velocity squared equals initial velocity squared plus 2 times that rate of acceleration times the distance traveled, and we're looking for final velocity squared here. That initial velocity is 0, it started from rest. We just found acceleration, and it says that the distance that it rolls is 10 meters. So we're going to have final velocity equals the square root of 100, or 10 meters per second. Remember, this is the case where it's sliding down, there's no friction. It's just like our old unit of dynamics. We use the net force in the parallel to find acceleration, and then we used kinematics to solve for this final velocity. Now things are about to get a lot more difficult. This time we're going to look as if the surface of the ramp and the ball are rough, so there's going to be friction, and that friction is going to cause the ball to rotate. You can't have a ball rotating or a disc rotating if there's no friction present. So we're going to use torque and force and kinematics to determine this translational speed of the ball at the very bottom of the incline. So I'm going to scroll down here, and we got a bunch of space to work with, and I'm going to redraw this picture for us where we have the ramp, and here's our ball, and we've got the normal force going this way. I'm going to break this into components. So this isn't a true free body diagram. Remember, the true free body diagram has the forces as they're acting, not the components. This is mg sine theta. We've got this one, which is mg cosine theta. And then the force of friction is acting this way. So it's going to be a similar setup. We're going to use the net forces to find acceleration. So again, let's switch colors. We've got the net force in the parallel is equal to, and in this time we have the mg sine theta here. That's in the positive down the ramp, and then we have to subtract our force of friction. Anytime we add up all the forces in a single direction, Newton's second law says this is mass times acceleration. So we come up with this here. And now our problem is that we don't know the force of friction. And if you scroll up, you see that we are given coefficients of friction, and you could use the coefficient of friction and the normal force and solve for it that way. But actually, because it's static friction, rolling without slipping is static friction. Remember that the force of friction is equal to, force of static friction is equal to the coefficient of static friction times the normal force when it's at its maximum. And we don't know if this is at the maximum or not, so it could be less than that. So we're actually going to use a different way to find torque, or I'm sorry, to find the force of friction, and that's through torque. So we can say, hey, our net torque is going to be equal to the moment of inertia times alpha, or angular acceleration, and the torque that's happening on this ball is just from the force of friction. The force of gravity acts from the center of mass, so its distance from the force to the axis of rotation is 0. So the force of gravity has no torque on the ball, but the force of friction does. So we're going to do the radius there times the force of friction is equal to the moment of inertia times alpha. And if we keep going here, we can say this is a sphere. It says it's a ball. The moment of inertia for a ball is 2/5 times the mass times the radius squared. I do have that memorized because I've used it so many times, but that doesn't mean that you should. You're either going to be given it to you on the test, or it'll be somewhere to use. So you don't have to memorize that. Take this a step further here, keeping the moment of inertia, and we want to use tangential acceleration because that's what we're going to use over on this side. So that is tangential acceleration over r. That's just how we go back from rotational to tangential. What you're going to notice here is that this radius cancels out all the way across, and you end up with that the force of friction is equal to 2/5 ma, 2/5 mass times acceleration. And it's this force of friction that we're actually going to use up here and enter into this equation. So we get ma equals mg sine theta minus the 2/5 mass times acceleration. Masses cancel out all the way across, and we got a weird thing here. We've got acceleration equals g sine theta minus 2/5 a. So we got to add this 2/5 over, and you end up with 7/5 a equals g sine theta. And if we solve this for a, we get acceleration equals 5/7 g sine theta. Now, I'll be honest with you, I just filled up this whole thing. I'm using a little bit bigger font, but all I did was find acceleration. I didn't even plug in the numbers yet. We'd have to plug in 10 for gravity, and our angle was 30 degrees, and that would give us the acceleration. But we wanted to figure out how fast is it moving at the end of the ramp, and so we had to find the acceleration, Then we'd go on and we'd type that in and do similar to what we did last time. The initial velocity was 0, the distance was 10 meters, we'd use kinematics and we'd solve for that. But because the acceleration is different, the final velocity would be different. And I'll leave that to you to figure that out on your own, solve it, see what you get, compare it with a neighbor, and see how that works out. The big problem, right? We had frictionless ball just sliding down. It was only the parallel component of the force of gravity that caused it to accelerate. And pretty simple. Sum of the forces, and then we used kinematics. In the other example, it was a rough surface, so there was friction, no slipping, so complete friction and rotation all the way through. And it was through the sum of the forces that we found acceleration, but in order to find friction, we had to talk about net torque. Okay? So the question remains, when should you sum up the forces? When should you sum up the torques? When should you sum up both? Well, you're going to sum up the forces whenever there is translational motion. So we're only talking about rotational dynamics. If it's in static equilibrium, sum of the forces is 0, sum of the torques is 0. If it's moving, if there's dynamics about it, not static equilibrium, you're going to sum the forces when you have translational motion only. You're going to sum up the torques when you have rotation. Rotation only. And then you're going to sum up both of them when you have both translational and rotational motion. So that first example, it was sliding down, only translational motion. You could imagine a ball rotating about an axis but not moving. That would be just rotational motion. And then the last example is where it's rotating and going down, and that's both. And that's where we had to use some of the forces and some of the torques. That's a tough problem, so you should feel good about getting through that, hopefully understanding it, and making some progress. So good work, and hope you enjoyed.